Okay, so here we are going to be looking at the law of conservation of linear momentum. Okay, so the law of conservation of linear momentum states that if the net external force acting on a system is zero, then the change in momentum is constant. The external force acting on a system is zero. The change in momentum is constant. So from Newton's second law, we have that F is equal to mv minus u all over t. Or we say that Ft is equal to m into v minus u. Okay, so Ft means change in momentum. Since the external force is zero, so you can say that change in momentum is equal to zero. Or you can say that initial momentum is equal to final momentum. Okay, that is important. That's according to the law of conservation of momentum. Initial momentum is equal to final momentum. Now, we have two types of collisions. We have elastic collisions and inelastic collision. An elastic collision is one in which there is no loss of energy after collision. Energy is not lost after collision. An inelastic collision is one in which there is a loss of energy. Okay? The energy loss can be in terms of sound, heat. When two things collide, sound can be produced, heat can be produced. That's energy loss. So, momentum of both elastic and inelastic collisions are conserved. Please note that. Even though their energies are not conserved, but their momentum is conserved, whether it is elastic or inelastic. So see a table here that gives us more differences. So elastic collision, energy is not lost. Under inelastic, energy is lost as sound, heat, etc. Under elastic collision, momentum is conserved. Under inelastic, momentum is also conserved in both. But under elastic, energy is conserved. Inelastic, energy is not conserved. Now, note that in a perfectly inelastic collision, they lose energy and are joined together. They don't just, after they collide, they join together, meaning that they move with what we call a common velocity after collision. Good. So, we're going to see different cases in applying this rule. Here, case 1, colliding bodies are moving in the same direction and they separate after collision. So, look at that. Before collision, you have m1, m2 with their initial velocities u1, u2. Then after collision, their velocities changes because after they collide, the velocity changes, m1, v1, and v1 to v2. So here in case 1, whenever after collision they separate, having different velocities, we can say that m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2, according to law of conservation of energy. Conservation of momentum. Initial momentum is equal to final momentum. Please note that. Now, the case 2 here says that in this case, the colliding bodies collide head-on. Head-on means that they move in opposite direction. They collide head-on, just like you see in the diagram here. Okay? They collide head-on and they separate after collision. In that case, because it's a head-on collision, momentum is a vector quantity, so we are going to subtract because they are moving in opposite direction. And but it is equal to m1 v1 plus m2 v2. Okay, so case 3 here has to do with colliding particles are moving in the same direction and they are joined after collision. That's inelastic, perfectly inelastic collision, and they move with a common velocity. So after collision and they move it, you can see that the initial momentum remains the same, but now because they join together and they move with a common velocity, the final momentum will be m1 plus m2 times v times their common velocity. Their velocity is common. Okay, now case 4 has to do with colliding particles are moving in opposite direction, that's head-on, and they join after collision. The head-on is the reason for the minus here. Okay, the initial momentum m1 u1 minus m2 u2, but because they are moving with common velocity, you have m1 plus m2 times v. Okay, question. Here says a body of mass 4 kg and moving with a velocity of 5 meters per second collides with another body of mass 10 kg and velocity 7 meters per second. If the bodies join together and move with a common velocity. What is their velocity after collision? Here we can see the solution. Since the bodies move in the same direction and move with a common velocity after collision, we can use this quickly. Okay, and that's m1u1 plus m2u2. The plus there is because they move in the same direction. Then equal to m1 plus m2 times v. V there is the common velocity. So m1 is 4. Your m1, the mass of the first guy here, is equal to 4. Then we have the v1, the velocity, the u1, sorry, which velocity is 5 meters per second. The m2, the second mass of it is 10 kilogram, and the velocity, let's call it u2, is 7 meters per second. So by the time we apply this, we are going to get that v is 45/7 meters per second. Now see another question here. It says a body of mass 2 kg moving with a velocity of 5 meters per second collides with a stationary body of mass 0.5 kg. If the two bodies move together after impact, that's common velocity. Calculate their common velocity. Now that's exactly what we have here. But here now the velocity of the second mass is 0 because it was stationary. So that makes it 0. So you see we have 2 times 5 plus 0.5 times 0 equal to 2 plus 0.5. Obviously my m1, the mass of the first guy here, is 2 kg. The velocity u1 is 5 meters per second. Then the mass of the second object here is 0.5 kilogram, and then the velocity here u2 is 0. 0 because it is stationary, it is not moving. You see the word here, stationary. Okay, that's beautiful. Now look at another question. It says a ball of mass 3 kg moving with a velocity of 15 meters per second collides head on. So whenever you see head on, you know that you must subtract their momentums in the opposite direction with a ball of mass 2 kg moving with a velocity of 20 meters per second. If the balls coalesce and move in the same direction, what is their common velocity? So you see the formula we use here, m1u1 minus m2u2 equal to m1 plus m2v. Okay, and of course m1 from this question here is 3 kilograms. U1, the initial velocity of the first guy, is 15 meters per second. Collides head on. The other mass here, m2, is 2 kilograms. Then u2 here is 20 meters per second. Okay, so we can find their common velocity, and we got it to be 1 meter per second. This is beautiful. Now this leads us, okay, let's stop here for now.